Welcome to The Explainer. Today, we're diving into a discovery from nature physics that honestly sounds like something out of science fiction. We're talking about scientists finding perfect cosmic-level order emerging from the absolute heart of quantum chaos. So let's just start with that idea, because it's a big one. What if perfect order could literally be born from pure chaos? I mean, that seems to fly in the face of everything we know. Usually, chaos just leads to, well, more chaos, right? But in the quantum world, the rules get really, really strange. You know, in quantum physics, there are these two concepts that have always seemed like total opposites. On one side, you've got topological matter. It's incredibly orderly, stable, and predictable. And on the other, you have quantum criticality, a state of pure, unadulterated chaos, full of fluctuations and just strangeness. Think of it like a perfectly serene, frozen lake versus a boiling, turbulent ocean storm. They just don't seem compatible. Let's dig into that for a second. First, there's the elegant, predictable world of these topological materials. They're defined by these fundamental properties that are almost unshakable. The classic example everyone uses is a donut versus a coffee mug. You can squish and stretch that mug, but as long as you don't break it, it'll always have one handle, one hole. That one wholeness is a topological property. It's robust, it's protected, it's orderly. And then, on the complete other end of the spectrum, you have the bizarre and chaotic state of quantum criticality. This is a truly weird state of being that happens right at a quantum phase transition. It is so chaotic, so turbulent, that the conventional particles that make up a metal, physicists call them quasiparticles, they completely lose their identity. They just sort of dissolve into the sea of intense fluctuations. Okay, so now let's introduce the star of our show, a heavy-fermion compound with the very catchy name CuRu4SN6. This material, as it turns out, has a pretty fascinating split personality. See, before this new research, scientists were pretty sure they had this material figured out. All the previous studies had established that this compound lived firmly in that chaotic camp. It was basically the textbook example of being intrinsically quantum critical. And the evidence for this was just overwhelming. I mean, the data showed something called a scaling collapse, which is a classic signature of this chaotic state. Measurements of its specific heat showed these wild fluctuations. Experiments showed zero signs of any magnetic order. The consensus was crystal clear. This was a strange metal where those well-defined quasiparticles just didn't exist anymore. It was pure chaos. But then, while studying this perfectly chaotic material, researchers found something that by all accounts just should not have been there. A clue that defied all logic. Okay, let's really dive into this contradiction, because it's at the heart of everything. We've got this material, CuRu4SN6, which everyone agrees is in a state of quantum critical chaos. So how on earth could it possibly be producing a signal of perfect topological order? It's like finding a perfectly formed ice crystal in the middle of a raging bonfire. It just doesn't make sense. And this became the central puzzle that the research team was determined to solve. So the first clue was this weird electrical signal. The paper calls it a spontaneous Hall effect. What that basically means is that a voltage was showing up sideways to the electrical current, but, and this is the key part, with no magnetic field applied. That's highly unusual, and for physicists, that's a major red flag that something interesting is going on. And here's the crucial point. This signal is a definitive fingerprint, a smoking gun, as they say, for a highly ordered topological state known as a Weyl semimetal. So somehow, out of all that chaos, a signal of perfect order was appearing. So how? How can both chaos and order exist in the same place at the same time? To solve this quantum mystery, the scientists had to figure out how these two completely opposite states were connected. So what they did was they started systematically mapping out the material's behavior. They were essentially tuning it, tweaking it with pressure and magnetic fields to see how these two states, chaos and order, were actually related to each other. And what they found is just beautiful. It turns out the topological phase forms a sort of dome that is centered perfectly on the point of maximum chaos. In fact, get this. The signal for perfect order was strongest right at the most chaotic point. This led to a mind-blowing conclusion. The chaos isn't fighting the order. The chaos creates the order. It turns out these two things don't just coexist. The intense quantum critical fluctuations, all that chaos, is the very thing that stabilizes and gives birth to this new topological state. The chaos is literally the parent of the order. I mean, that is a complete paradigm shift in how we think about these things. So this finding, it doesn't just solve one little mystery. It actually helps us build a completely new understanding of physics. This isn't just about one weird material. It forces us to rethink how topology itself even works at the quantum level. And this forces us to ask a really fundamental question about how topology even works. I mean, remember, those fundamental particles, the quasiparticles, they've dissolved into a chaotic soup. So how can you possibly have order when the very building blocks that are supposed to be ordered are gone? Well, the answer seems to be that we need to expand our definition of topology. The old way of thinking absolutely required stable particles and their energy levels to define it. But this new way shows that tautology can come from something even more fundamental, from the underlying symmetries of the system. It's a way to see order in the possibilities, even when the actual particles are a complete blur. Think of it this way. Even in that chaotic soup of particles, the rigid, symmetric structure of the crystal lattice itself acts like a kind of scaffold. This underlying grid forces a certain order onto the chaos, preserving these topological properties even when the individual particles have completely lost their identity. So what you should really take away from all this is that it isn't just a one-off curiosity. It's not just a cool science story. It's a blueprint. The paper actually proposes this as a new design principle for discovering the next generation of quantum materials. Step 1. Find a material that's teetering right on the edge of quantum chaos. Step 2. Look for signs of a new topological phase being born directly from those chaotic fluctuations. And this could be a really, really big deal. The authors suggest this new search strategy could be just as fruitful as the hunt for unconventional superconductors, which famously also tend to pop up near these quantum critical points. We might be on the verge of finding a whole new class of materials with all sorts of exotic properties. This work really does open up a whole new frontier. It's transforming what we all thought was just random noise into a signpost for discovery. And it leaves us with this incredible, tantalizing question. How many other new materials are out there, just waiting to be discovered, hidden in the very heart of quantum chaos?